Hi everyone and welcome back to a new series AI concepts with coding from scratch. This is the first video in this series and in this video we are going to discussing about the UNET architecture from the scratch using Pytorch and Python. So without wasting time, let us start the tutorial right now. In order to building one UNET architecture from the scratch, we're going to be using here the Pytorch. So first what I can do, I'm going to import the Pytorch first. So it should be the import torch in Python. That's a torch torch. And then I'm going to be importing here the torch.nn module because I'm going to be using here the neural network here. So let's say import torch.nn as nn. And also I'm going to be importing here another library called the pillow because I'm going to be using here one image for testing that you can see on here. So I'm going to import from pill. I'm going to import here the image. Okay, it should be the capital image. Okay, then I am going to simply print in the version of the torch that I'm actually using it here. So I can using here the print statement to see the version of the torch that I'm using. Let's say torch dot underscore version. Okay, this one. And I'm going to save it and I'm going to run it from here. You can run it from the terminal as well. And now you can see it's loading. And you can see I'm using 1.7.0 with Coda 10.1. Now let's go on the paper. So this is the paper called the UNET, Convolution Networks for Biomedical Image Segmentation that you're going to use it for here. And if I go down, then you can see one network architecture. It just look like that. So why it's called the UNET? Because it's look like the U shape that you can see. So it's just having some convolution layer with having some ReLU activation functions. And also you can see here the max pooling in the from up to cross true. And then it having one up convolution layer that's nothing but the convolution of the transpose 2D. Then we have the convolution 1 cross 1. So this is nothing but the sign of that. You can see this color is below. It's nothing but called the convolutions. So it will taking one input size of 1 and output is nothing but 64 cross 64. And this is nothing but my input image style and which I'm taking 572 cross 572 images. And after that one single convolution, it will actually downsampling this one and 570 cross 570. And again it's down convolution this one and it's right now 568 cross 568. So we're using the two double convolution on here. So that's been one convolutions and two convolutions. And after that we're having adding one max pooling. You can see this is nothing but the max pooling layer. This is the max pooling, right? And after that what we have the same thing. It's nothing but at the input. And now after importing this one, we got in the output as called 128 cross 128. And same thing, we have the double convolution layer. You can see inside this section we have the double convolution layer. And after that you can see same thing, we are applying here the max pooling. Then max pooling, that's mean we have 1 2 3 4 and the 5 double convolutions. Okay, 5 double convolutions with having the 4 max pooling layer. Okay, that's when it will actually downing the size of the images. And after that you can see here we applying here the up convolutions. Okay, up convolution, but we having the double convolution on here. That's mean we have double convolutions, max pooling, double convolution, max pooling, same thing up to here. And after that we have the up convolutions and with having another double convolutions, up convolution, double convolutions, up convolution, double convolutions. And you can see here the size of the image size is increasing. Now you can see here 28, this 28, now it increasing to the 54, 52, and same thing, it will increase in the size of the images. And after that we got in here 64 cross 64 as our input size. As well as you can see here the image, the sum of the portion is nothing but coming from this side. Okay, you can see this portion after 5.1 to 5.1, this portion is coming from this side. That means this is crop and crop. That's mean you need to crop some images from here to here. Okay, you can see some one interconnections. And if I go down to the network architecture text, and you can see here this is nothing but one images. When cropping this out, we don't have any padding. That's mean image size should be reduced. And if I go down, then you can see one section that's called the model architecture. I mean, through network architectures, and it's consisting a contracting path. I mean, left side path is called the contracting path, and the expansive path is called the right side path. So the contracting path follows the typical architecture of the convolution network. It consists of repeated application of 3 cross 3 convolutions, 3 cross 3 convolution. Okay, and one unpadded convolution. That's means no padding in on here. Each following by a rectified linear unit that's called ReLU activation functions, and 2 cross 2 max pooling operation with straight up 2. Okay, straight up 2. Dekho. Therefore, downsampling. For downsampling, each downsampling step would double the number of features channel. Okay, every step in the expansive path consisting of a upsampling for the feature map followed by 2 cross 2 convolution for the up convolution. That means this is nothing but the part for the right side part. So let's try to building our left side part. Then we're going to come again in the paper. So what I can do, I'm going to go on here and try to closing this out, and I'm going to removing this out, and then I'm going to simply going to creating one class for the UNET. So let's try to creating the class. Let's say class equal to call UNET, and then inside that I'm going to inherit the nl.module. If you know the basics of the Pytorch, if you need the Pytorch tutorial in one shot, so comment down below. So then I'm going to using here the def. Let's say def init, and inside that I'm going to passing here the self, and then I'm going to creating here the super keyword. So let's say super dot underscore underscore init and self, and okay, don't passing the self on here, we can pass it to the super because you're going to take in the input as image. Let's say in UNET and the self, and then that's our ready. Our class is ready. Now what I can do, first I'm going to adding here one max pooling. I mean building here the max pooling, and after that we're going to building our double convolution layer in a functions. So what I can do, let's say self dot, and we can using, let's say max pool. Okay, let's say max pool. Okay, and then I'm going to using an nl dot max pool. Okay, let's say max pool 2D, and inside that I can give it the kernel size. So let's say kernel and the size is nothing but the 2 that we see on our architecture, right? And then to giving the stride equal to 2, let's say stride equal to 2 is nothing but for the max pooling layer, stride equal to 2. And after that what I can do is simply going to creating the double convolution. If I go on the paper, so you can see we have the max pooling layer with a stride of 2, that you can see stride of 2. So that's why you give it here the stride equal to 2, because just we following the paper. Then after that, you need to adding here one double convolution layer that we see in the architecture. If I go on here, we having one double convolution layer that you can all see on here. So you're going to simply going to add, creating here functions for the double convolutions. So for that, what I can do, I need to create one function that's been defined a method. You can say in the Python because it's object-oriented programming language. Let's say double convolution. Okay, convolution. Okay, let's say convolution layer. Then it's on taking one input channel. Let's say input underscore channel, and then it will taking one output channel. Okay, output channel, and then nothing else. Now what I can do is simply going to creating one sequential method, because this is one sequential layer. That means it is passing this data from this layer to this layer. So that's why this is one sequential layer, and this input should be taken as the output, and this output should be taken as the input here. Okay. So now what I can do is simply going to creating here nn dot sequential. Let's say sequential, and inside that is simply going to passing here. Let's say nn dot con 2D, because this is a convolution layer, and inside that we're giving here our input channel. So let's say input channel. Okay, not input prompt, actually input channel. This is coming from the parameters. Then we have the output channel. Then to give it here the kernel size. So kernel size is nothing but the three kernel size, because we see in the network architectures, you can see we having 3 cross 3, right? 3 cross 3 convolution there with unpadded convolution. That means we do need to give in here the padding is same as well. And then we're simply going to adding here the ReLU activation functions. That's a ReLU, and then inside this ReLU we're simply going to make in place equal to true, in place equal to true. And after that what I can do is simply going to creating here the another convolution layer. So because this is the double convolution, let's say conv 2D, conv 2D. Okay, conv 2D is not coming on here, but why? Okay, just because of we don't give it a comma on here. And now inside that this output, this channel output is coming to the as input of the double convolution. The next convolution layer, so it should be the output channel. So let's say output channel, and then we have to give it here the output channel as well. Let's output channel. So output channel kernel size, let's say kernel size is always 3. And then we are adding here one ReLU activation function. Let's say ReLU. Okay, ReLU. Okay, ReLU, and inside that you can passing here in place equal to 2. Okay, now our double convolution layer is ready right now. Now we can simply going to calling this out in our code. So what I can do is simply going to calling this out. Let's say self dot, it's nothing but the down convolution. Let's say down con, let's say down conv 1, and then you can using here this double convolution. Let's say double convolution layer, and inside that you can passing here 1 comma, let's say 64. Okay, 1 comma 64. Now what I can do, we're simply going to adding all of the layer for that. So we having how many layer we have? If I go on here, we have the 1, 2, 3, 4, and the 5 layer with corresponding the 164, then 128, 256, 512, and 1024. So what I can do is simply going to copy this out. We're simply going to copy this out, and then I'm going to pass it to the 5 times. Let's say 2, 3, 4, and the 5. Okay, so it should be the 2, and it should be the 3, and then it should be the 4, and it should be the 5. Okay, again, if you see in the architecture, you can see it's 64, 64, 1 into 64, and this is nothing but coming in here in the max pooling. That's mean it just having one max pooling, and we had the 128, 128. So what I can do, we're simply going to pass it here. Let's say 64, okay, cross 128. Let's say 128, okay, and after that, what we have the 128. Let's say 128, and with having the 256, 256, and then we have the 256. Let's say 256, and then we have the 256, and we have the 512. Let's say 512, and the 512 is nothing but having the 1024. Okay, just we adding here the double convolution, but we're not adding here the max pooling on here. That's mean we're just creating the building block or the max pooling. This max pooling you already built it, and this one to 64, and then 128 to 64 to 128, and 128 to 256, and 256 to 512, and 512 1024. Now let's creating here our forward method. Okay, now what I can do is simply going to creating our forward method. So let's say def of forward. So we can pass it. Let's say def equal to forward, which one taking one x. So you can passing here the x or images. What are let's passing here the images. So let's say image, and then what I can do is simply going to creating here. Let's say x1 equal to self dot down. Okay, that's a down convolutions layer of the okay one, and inside that is simply going to passing here our images, and then we're simply going to adding here one max pooling layer. So we can adding here, let's say self dot, okay, self dot max pool, and inside that you can passing here the x1, this one, and this was nothing but the x2, and this one taking one image. So this one taking one image. So to also calling this out, let's try to first printing here, let's say x1 dot size. Okay, okay, so what I can do, I am simply going to calling it out. Let's say if name underscore main, then we're simply going to import one images from our directory. So for that we're going to import from torch vision, because we're going to using the torch vision as well to transform it with the size of 572 cross 572, and I'm going to importing here the transform. Let's importing here the trans forms. Okay, now what I can do, I am simply going to load the images using this payload library, and after that I'm going to do the transformation. So let's try to give it here. Let's say first create a variable called image path. Let's say image underscore path. So our image is nothing but on here, that's called file.jpg. That's our image that we're going to use it here. So that's called file.jpg. Let's say file.jpg, and after that I'm going to use the payload library to actually open the images. Let's say image.open, and inside here I'm going to passing here the image path. So image underscore path. And also one more thing, if I see on the architecture, you can see this is nothing but taking one grayscale image. You can see here just it having the one channels. So we're simply going to convert them into the grayscale. Let's say convert, okay, convert into, let's say unity. If I passing here the L, so it'll convert this image into the one channels, and this is nothing but the image. Let's say image, and after that what I can do, you need to do the transformation. So I'm going to using here transform. So let's say transform dot transform dot compose, sorry, compose, and inside the compose, and inside this compose, so what I can do is simply going to passing on list of items just called size and the tensor, because it also convert them to tensor if I need to passing this inside our unit architectures. So you can using here as a transforms, okay, okay, dot resize, and resize, and inside there I'm giving here in the tuple format, let's say 572 cross 572. Okay, and after that we need to also convert them into the tensor so that we can pass it to our architectures that we created. Let's say transform dot to tensor. Let's say to tensor. So to tensor, and inside that we don't need to pass in anything else. It's automatically convert them into the tensors. You can use here the numpy tensors here. You can also do that, but it will give you some kind of error because you're coding in the Pytorch, so you can using the matrix in the form of the numpy. So this is nothing but my transform. So I can make it, let's say transform. So our image is ready right now, but the problem is the image it is taken by the UNET is nothing but in the form of bath size, in the form of bath size, okay, in the form of bath, 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 bath size. Then you have the channel, okay. Then we have the width or height. Let's height. Then you have the width. Okay, so the Pytorch, I mean, our architecture is nothing but taking the image based on this because this is also one convolution layer. We need to reshaping this out. So we need to first go into creating here, applying here the transform inside our images. So let's say transform equal to image, and then this is nothing but my image tensor. Let's say image tensor, okay, image tensor. Now what I can do is simply going to give it the batch size. So because we're going to loading here just one images, so our batch size is nothing but the one. Let's initialize this one. Let's say batch underscore size is nothing but the one. And then after that I'm going to convert it in the unsequence. Let's say image tensor dot unsequence. So let's say okay, let's say sequence. Let's say just image tensor, right? So let's say unsequence. So SQE EEGE on sequence of 0. Now it will getting here one batch of images, then it having the channel, it having the height and the width because we're using the unsequence just like the expand dimensions in the numpy. Okay, then after that what I can do, this is nothing but my image tensor as well. So this is my image tensor and I'm going to make it here. And after that, I am simply going to adding here the batch size. Now it is just converted into one channel like that. Let's say one comma, then we have the channel, then we have the height, then we have the width. Okay. So, but we don't adding here. Okay, we're not also adding here one more thing that's called the one as well. Batch size, comma one, comma channel, comma height, and the width. That's when we converted this one comma channel comma height and the weight. Now we need to adding here the batch size. Okay, that's mean how I'm actually using the unsequence, it is converting this one like that. Now we're simply going to adding here one batch size. So for that I'm going to using here image tensor. That's the image tensor dot repeat, and inside that I'm going to passing here the batch size. So that's the batch size, and then I'm going to using here 1 comma 1 comma 1. Okay, now it will adjust the batch if it is necessary. Then this is nothing but my image tensor. Let's say image tensor, and now I am simply going to pass it to our model. So I'm going to creating here, let's say model is equal to UNET, and then inside that I'm going to printing here the unit. So let's do printing here the model of UNET, and inside that I'm going to passing here the image tensor. That's the image tensor. Now I am trying to painting the size of the x1 because this is nothing but the following one done convolutions layer. Okay, just one single done convolution layer, and after that we apply here the max pooling. Let's try to first printing here our x1 so that you can see that our double convolution working very fine. So I'm going to printing this out from here. So we have the image size of 572 cross 572 with having one channel. Oh, okay, it's called a by 2 is given. Okay, in it takes one position argument, but two are given. But why two कितने दिया मैंने भाई? Okay, it will give it here the depth of init. We're just adding here another module, and inside the self we're adding a self and the self dot init. So let's try to checking this out. Okay, it's the image tensor, right? We're just adding here the image tensor. So why this kind of error? So okay, you need to okay, we need to passing here. We're just adding here the unit again. So that's why this problem, because we already initialized the model, right? So why should we passing here the unit as well? Okay, let's try to run it out. because you already initialize the unit, right? Non type object is not callable. Okay, non type object is not callable. So any problem on here? Okay, the problem is actually happening on here because we're not returning anything else. So that's why num type object is not callable, because nothing is actually coming on here. So to return here one statement, let's say return here. Let us store it inside a variable called, let's say, con, and then I'm going to returning this one because it's not returning anything. So obviously it give me the error. Okay, the spelling is also incorrect. So let's say it should be double convolutions. So it should be the double convolution layer. Let's try to changing it on here, and then I'm going to replace this one. Okay, and then after that, what I can do, I am simply running this one. Let's try to running this on here, and then you can see, just to wait. Okay, you can see here 64, 568, 560. Let's go on the paper again. There's a paper. Now you can see here 64, and now you can see 568, 568. That you can see on here, right? Cool. That's been 568, 568. After one convolution layer, we have got here the size of the images is called 568, 568, and other the 64 is nothing but our output channel, right? Now what I can do, we simply going to adding all of this layer. So what I can do, we have the down convolution of the image, and now we simply going to passing this max pooling. If I see on here, passing this max pooling as the input of this channel, of the next channel. So what I can do now, we simply going to adding all of them. So uh, we can passing to our forward method because we already implement the max pool, right? So we passing this x1, let's say x3 is equal to self dot down. Okay, down convolutions layer of the 2, and inside that what I can do is simply going to passing here the x2, right? The x2, it's coming from here, right, from the max pooling layer. So we can also come, let's say, export equal to self dot max pool. Okay, max pool of the is coming from the x3. Okay, it's coming for the x3. Okay, so we can again, let's say x5 is equal to self dot down convolution layer of the 3. थोड़ा स्लोली करना पड़ेगा एक्सपोर्ट, क्योंकि यहाँ पर बहुत मिस्टेक हो जाते हैं क्योंकि इट्स सीली टैक्स. Okay, so let's say x6 is equal to self dot max pool. Okay, that's called max pool, and inside that we're passing here the x5. Okay, okay, max pool inside the x5, and then we're getting here the x6. Let's say x okay, it should be the x7 is equal to self dot down convolutions of the 4, and inside that we're passing here the x6, and then x8 should be the self dot down convolutions of the 4, and inside that we're passing here the x7, right? And then we're having one max pooling. So x9 equal to self dot down convolution. Okay, this should be the max pooling, and this is the down convolutions of the 5. Okay, let's say this is the x8, right? So it is the x8, this is the x7, this is the x8, and this is the x9. Let's try to paint in the shape of the x9 and try to see this one as like the architectures. Okay, so we got 1 comma 10242828. Let's go on here, and we got 10242828. Cool, that means this part is done right now. Now what I can do now is simply going to creating here this up convolution one. So for this case, you're going to using here the con transpose 2D because this is the up convolutions, and in convolutions it will decrease the size of the pixel, and the up convolution it will actually increase the size of the pixel. Now we simply going to first creating here the first layer. This is for the up convolution layer. So I need to go on here inside our architectures, and then I'm going to creating here our convolutions layer for the off. Okay, so what we have, we having this is called the expansive path. Let's expand path, expansive path, and then this is the right path, right? And we have the left path. This is called the contractive path, right? So let's say contracting, let's say contract starting path. Okay, okay, let's try to comment this down. Now let's try to adding it out, but before that let's go on the paper. So in this paper you can see it just having one up convolution layer, and following by it having that two double convolution layer. That's been doing to creating the functions again for this one. This is just having one up convolutions, and if I go down to the network architecture, then you can see for the up convolutions, okay, every step in the expansive path consists of a upsampling of the feature map followed by 2 cross 2 convolutions, up convolutions that half the number of features channel, a contractions with the corresponding cropped feature map with the contracting path having 3 cross 3 convolutions is followed by a relativation functions. Thus we need to creating here two things. One is the up convolution layer, then also one cropped and cropped. Okay, because we need to joining this one. So what I can do, I need to go on here and let's start to creating here our expansive path. So this is, let's say, self, and let's say up, let's say trans. Okay, because this is a transport 2D, let's say up transpose to 1, and you're going to be using here nn dot conf conf transpose 2D, and inside that you're passing the input channel. So input channel is nothing but our, okay, it should be a small input channel is nothing but the 1024. If I see in the architectures, you can see here this is passing as the architectures that you can see 1024. You can see 1024 is going to passing through on here. It's an input channel, and the output channel is nothing but is 512. So what I can do is simply going to go on here, and then you have the out channel. Okay, it's the in channel, sorry, no, it's input channel. It should be the in channel. Okay, in underscore channel, and then we have the out underscore channel. So let's say, let's go on the next line. Let's say out, and it should be the out channel. Okay, out channel is nothing but the 512. Cool. Now after that, what we have, we need to creating here. Okay, we need to, okay, why this error? Expanded, okay, by length, okay, into removing one things, and then we're using here the kernel size. So let's say kernel size of, let's 2, and then we're using here the stride equal to 2 that is mentioned in the paper. Now what you need to have, you need to also adding here the double convolution layer followed by this one. You can see you just need to adding here one double convolution layer on here. So we can adding here, let's say self dot up convolution layer other one, because yeah, you know that this is a double convolution, but it's nothing but in a half up thing. So that's why I'm making it, let's say, up convolutions one, and inside it you're going to calling here our double convolution layer that you actually created, and inside that you can be passing here 1024 and 512. 21 and 512. If I go on here, you can see here it's following by this one, and with having this count of the 3 cross t with having the ReLU activation functions, right? Now we simply going to adding all of the layer as well. But before that, let's try to add it to our forward path so that we can also see that how the crop and the crop is actually work, because we need to cropping the pixel size as well. So we can simply going to go on the forward path and try to implement this one. So for the right path, I mean the expansive path, we don't need to actually creating here this all this variable. We can do it in just one single variable as well. So let's say x1, let's say x1 is nothing but coming one layer of the transports. Let's say x, we can just making this x. So let's say self, okay, self, and then you can using a self dot up transpose of the one. Then inside that we can passing here the x9. We're going to passing here the x9, and then we have the, let's say, x1. So x1 is nothing but the self dot, then we having falling by, we don't have any max pull, right? We don't have any max pull. We're just having the uh, up convolution layer, right? We just having the up convolution layer. So what you can do is simply going to pass it, let's say, up convolution layer the one, and inside that we passing here the our x. Now let's start to printing here the x1. Let's start to printing here the x1. Okay, let's start printing the x1 and x1 dot size. So x1 dot size. Okay, and then I'm going to painting it here first. Let's see this one, the how the x1 size actually look like. Okay, and you can see here just giving me some kind of error because this is not match. But why it's not match actually on here? That's only to do the cropping. Now let's try to do one more thing. That see, when applying the cropping, you need to using it here for this x7 path. If I see on here, let's say this is the x1. This is not this one. If I go on here, this is the x1. Okay, let's say this is the nothing but the first, and we have the second. This is the second. This is the third. We just talking about the connections, right? And this is the fourth. If I see on here, this is the fourth. And if I see that this is the fourth one, the fourth one is connected to this one. You can see the crop one. In here you can see the size of this matrix is nothing but 64 cross 64, but here is 56 cross 56. That's when he joining this matrix it not matched, because the size of the matrix or shape of the matrix is not matching. Okay, so it's try to, if I try to painting this one, so what I can do is first apply here the up transport, because this data is coming from here. And if I try to printing here, let's try to removing this one now. If I try to painting here the size of the x, let's say x dot size. And if I try to painting the size of this x7, because we need to concatenate this x7 with the x, that is seen the architecture. You can see the architecture here. This path is and same of the portion is nothing but coming from the x7, this x7. And now if I try to painting here the size of the x7, then you can see just one more thing, and just a white, you can see one more thing, that is nothing but the size of the matrix is nothing but the same. That's why you can concatenate them. You can see it's nothing but the 56 is nothing but for this after this up convolution layer, and the x7 size is nothing but 64. X7 function is nothing but 64. So how can you join them? Yeah, we're creating here a function which will actually help us to do the cropping. Let's call the center cropping. So let's try to do the crop. Let's say crop. Let's say image, or you can say let's say cropped and cropped, whatever you can actually give it in here. So let's say cropped image, and then inside that you can pass in here the original tensor, because we're cutting the tensors. So original tensor, that's our target tensor. So our target tensor is nothing but our is coming from 5 6 and the 5 6, and to making it with the size of the 64 cos 64. Now that's our target tensor. Let's try to make it. Let's say target size. Our target size is nothing but based on our target tensor. So let's say target tensor dot size of the 2. So it can taking the size of that, because it's nothing but falling off this 1,572 cos 572, with having the, sorry, 5 not 570 actually, is falling here 1 comma 570 cross 64 cross 64. So just taking the 64 one, I mean the last channel of the 0 1 2 like that. And then after that into taking the size of the tensor, that is nothing but our original tensor. So tensor dot size is nothing but our original tensor dot size, and we're taking the tooth channel. That's mean if I try to painting this one, let's try to return, okay, no, don't need to return something else, what I'm talking about, क्योंकि गगा खिचड़ी हो रहा है ना, इसलिए आपको समझ नहीं आएगा, इसलिए मैंने दोबारा रन कर दिया इसको. सो लेट्स कॉपी दिस आउट. देखो ये दो चीज मैं कॉपी करता हूँ इससे, तो इससे आसान हो जाएगा. कॉपी हो गया क्या? Okay, let's try to pass it here. So see, toss the size is not but 1 5 1 2 5 6 and the 64. So to convert them into the 64 to the 5 6, right? Like that, like that. So what you need to do, this is the size. So how can extracting the size from here? So you can using the size method, just getting this one, and after that you can got 1 cos 5 2 5 1 2 64 64. So this is the 0 index, 1 index, and the 2 index. So you can taking this one, because this image this 56 and this 56 is same, you can take it 3 as well. Okay, it's up to you. So you're taking the 2, that's when you got here the 56, and for the tensor size you got the 64. Now what I can do is simply going to uh, uh, actually minus it from here. That's a tensor size dot target tensor. Okay, so target size, sorry, not target tensor, target size. Okay, okay, target size. So this is nothing but our delta. That's our delta tensor. Okay, now what I can do is simply going to divide them by 2. That's a delta tensor divided by 2, so that you can get the integer. So let's say delta tensor in the same variable, and then we're simply going to uh, uh, creating it for the original images, the original tensor. Let's say return the original tensor, and inside that you need to taking the all of the uh, thing that's called 1 and the 512. I mean this one 1 and 512. Then after that you can passing here this delta tensor. Let's say delta tensor, and then from the delta tensor you're taking it from the tensor size. That's a tensor size minus delta tensor. Okay, minus the delta tensor. Now it's converted to this one. I mean, we're just adding this 562 with this exit columns. Okay, and then to do this thing for here, that's a delta tensor, and you can now copy this out from here. Okay, let's call delta tensor. Okay, same thing on here. Now it's converted to this portion. So you need to add it to, okay, you need to add it to the list because this is the concatenate path. I mean, it's using just location iloc, just like the iloc in the pandas or numpy, whatever. Now let's try to using this cropped image, and this is nothing but, let's say y equal to, let's say y equal to, and then you're going to call in this cropped image, let's say cropped image, and inside you're going to passing here the x7. Now after that, what I can do is simply going to concatenate this one. So we're simply going to using here, let's try to paint in the shape of the y first, and then we can see this one because it's taking the x7, right? Okay, if you like this video, just comment below and subscribe our channel. Okay, it's called the target size. Okay, so okay, target size, you need to give it here the x7 and the comma x. So that's why, because target size is missing. Based on the size, you need to actually making this out, right? Because this is a up convolution. I mean, main reason you could convert them into 5 6 cos 5 6. Now we got here 5 6 cos 5 6, right? Now we can simply going to add it down, and we're simply going to passing this inside our up convolution. If I see on here, to passing this inside our up convolution layer. So we can passing this on, let's say x equal to self dot, and we can pass into this up convolution layer 1, and inside that we need to passing here touch dot cat concatenations, and inside that we need to passing here in from of the x7. Okay, not x7, x and y, because we already concatenated this one, and you can simply passing here this one. Now if I try to printing the size of the x, that you can see, let's try to printing this one, and then we can see the size of the x, the last one you can see 512 5252. If I go on architecture and 512 and 512 5252, you can see 5252. Okay, so we can got it here 5252. Now following this one, how many layer we have? We have 1 2 3, rest of them, that has been 4 uh, up convolutions having the double convolutions layer. So we can simply go into uh, copy this out, copy this, okay, not this one. Okay, you need to remove this one, we need to paste it here the 3 times. So 1 time, 2 time, and the 3 time. Okay, let's try to make it in the real format, and then this is the x9, right? And now uh, this x9 is passing to this x7, and then we need to passing here the, without x, we need to passing here the x, because this is x. Now this is converted to the x5, that you can see on here. This is x5 and the x3. So we don't need to convert anything else on here, just you need to convert in this x5, and this is same thing called taking the x, and this is the x number 3, and this is the x number 1. Okay, now we can simply going to printing the size of the x. Now instead of printing here the x dot size, and then we can simply going to printing this out. Now let's start printing this out, just printing a statement on here. Okay, and also you can got the output as well. So you can got, okay, we have uh, some error on here. So let's try to checking on here what kind of error we got. Okay, we need to also changing this one with the convolution layer of 2. Okay, because we create it out. Okay, not creating this out, so we need to creating this out as well. So we need to passing here the 3 times, right? 3 times, and let's try to making it out, because yeah, we convert this one, but it's not actually initialize this convolution layer. So it's nothing but the 2 and it 2 and it the 3 and it the 3 and it's the 4, it's a 4, and as well as it's the 4 as well. And then we need to also changing the size of the kernel. So what I can do, I need to go on this 2. So this 512, it should be the 512, and it should be the 256, 2, oh, 256, and this is also 512, 256, and this is taking as 256 and 128, and this is the 256 and 128, and this is the 128 is following by the 64, and this is the same thing is 128 and the 64. Okay, we have the combination layer. Now we can also add in here the last layer. This is nothing but our output channel. Let's let us add it later on, but let's try to checking this one is really working or not. Okay, so this is the 1, and then to convert them into the 2, and this is for the 3, and as well as this is for the 3, and then this is for the 4, and this one for the 4 as well. So let's try to now run it out. Okay, let's running this out and try to check. Okay, we need to also do some changes on here or not. Yeah, we changes everything on here. Yeah, now it's loading. Now you can see, okay, again error. So see what the error is actually got is the transport number 4 is x9. Okay, oh, is the x, is the x. Okay, again. Okay, that's why this problem is actually happening on here. Okay, actually going for the deep to deep because it's really taking time to understand this model. Okay, we got here 164, 388, 388. Okay, if I go on here, we got 380 cross 380 is nothing but my pixel size, and 64 cross 64, but okay, 64 cross 64. Now we need to adding here this last layer, this called the output layer. So now let's try to adding here the output layer as well. So what I can do is simply going to adding here, let's say self dot out. Okay, out is nothing but call nn dot, this is nothing but a convolution layer. It's a con 2d, and if I see on here, uh, okay, it's convolution of the 1. Okay, 1 cross 1, that's a kernel size is 1. So we can give it here, let's say in channel, let's say in channels is nothing but the 64, and the out channel is nothing but our 2, and the kernel size is nothing but the 1. Let's say kernel size is nothing but the 1 that we mentioned in the paper, right? Now we're simply going to adding this output to our output. So it can be the x equal to self dot output if passing this output as well. So now we can simply going to returning here the x on here. Now let's try to running this out and try to checking the shape of that just for printing this one. Now we can see we just having one output matrix with size of 1 cross 2 cross 380 cross 380 that you can see on here. That is on 2 and 38 cross 38. Okay, that's our output segmentation map that we get on here. We also adding here our tensor. It designed actually this our segmented actually tensor that you can see on here. So that's all about the unit architecture. So that how can actually building the unit architecture from the scratch, and you can also use it for the segmentation tasks as well. But in this case, we are not going to training this model with the real-time images, but in the upcoming projects, I mean upcoming projects in our multiverse series, we try to add in this one because this is the another series for the AI concept and coding from the scratch. So that's why in this series we are not adding here the model training. So we're simply going to adding here in our project series. I mean, we're going to using this unit architecture to for the segmentation tasks. Okay, so that's it for today now, and hope you enjoy this series, enjoy this video. So share with your friend, boyfriend, girlfriend, whatever else who are learning the machine learning, deep learning, and the artificial intelligence. So share with them. So I'll be back with the another tutorial in the series, and just hit the like, and we deserve 100 like. Okay, so thank you and bye bye.